Hi, I'm James Anderson, your host, and today we're going to discuss how life on Mars would look like for humans. Human curiosity and the relentless pursuit of knowledge have driven our species to explore the unknown. This quest has taken us from the depths of the ocean to the far reaches of space. One of the most tantalizing frontiers in our exploration of space is Mars, the fourth planet from the Sun, and a world that has captured the imagination of scientists and the public alike. The prospect of human life on Mars raises numerous questions about survival, adaptation, and the future of humanity. This episode explores how life on Mars would look like for humans, covering aspects such as living conditions, technology, social dynamics, and the long-term implications of establishing a human presence on the red planet. Mars presents a series of environmental challenges that are starkly different from those on Earth. The Martian atmosphere is composed primarily of carbon dioxide, about 95%, with traces of nitrogen and argon, and only about 0.13% oxygen. This means that humans cannot breathe Martian air and would need life support systems to provide breathable air within habitats and suits. The average surface temperature on Mars is around 80 degrees Fahrenheit, minus 60 degrees Celsius, with temperatures varying greatly depending on the time of day and location. The thin atmosphere offers little protection from solar and cosmic radiation, posing a significant health risk to humans. To mitigate these dangers, habitats on Mars would need to be shielded from radiation, either by using materials that can absorb or deflect harmful rays, or by situating living quarters underground or within natural Martian formations. Building habitable structures on Mars would be a monumental engineering challenge. Initial habitats would likely be prefabricated modules transported from Earth and assembled on Mars. These structures would need to be airtight, insulated, and equipped with systems for temperature regulation, air filtration, and pressure maintenance. In the long term, in-situ resource utilization, ISRU, will be crucial for sustainable living on Mars. This involves using local materials to construct habitats, produce oxygen, and generate water. Martian regolith could be used to create bricks or concrete for building structures. Water, which exists as ice beneath the surface and in the polar caps, could be extracted and purified for drinking and other uses. Electrolysis could split water into hydrogen and oxygen, providing breathable air and fuel for rockets. Sustaining a human population on Mars requires a reliable food and water supply. Initially, food would be brought from Earth, but this is not a sustainable long-term solution due to the high costs and logistical challenges. Therefore, developing a closed-loop life support system is essential. This system would involve growing food locally using hydroponics or aeroponics, which allow plants to be cultivated without soil by providing nutrients directly to the roots through a water-based solution or mist. Mars regolith could potentially be used as a growing medium once it has been treated to remove toxic chemicals like perchlorates. Researchers are exploring the possibility of using genetically modified plants that can thrive in Martian conditions. Water recycling systems would also be vital, repurposing wastewater from various sources, including human waste, for use in irrigation and other needs. Efficient transportation on Mars will be crucial for exploration, resource extraction, and the establishment of a functioning society. Rovers, similar to NASA's Curiosity and Perseverance but scaled up for human use, will play a vital role in early missions. These vehicles will need to be pressurized and capable of long-range travel, equipped with life support systems and robust navigation technologies. As the Martian infrastructure develops, more advanced forms of transportation could be introduced. This might include magnetic levitation trains running on tracks laid across the Martian surface, or even aerial drones for quick reconnaissance and cargo transport. The development of reliable transportation networks will facilitate the expansion of human presence on Mars and enable efficient movement of people and goods. Sustainable energy production is another critical factor for life on Mars. Solar power is a viable option given Mars' relative proximity to the Sun, although the intensity of sunlight is about 60% less than on Earth. Solar panels would need to be efficient and resistant to Martian dust, which can cover and degrade their performance. Innovations like dust-resistant coatings or automated cleaning systems would be necessary to maintain energy production. Nuclear power is another potential energy source. Small modular reactors could provide a steady and reliable power supply, unaffected by the planet's weather conditions. These reactors would need to be safe with robust shielding to protect inhabitants from radiation. Wind power, although less effective due to the thin atmosphere, could also supplement energy needs, particularly during dust storms when solar power generation might be compromised. Communication with Earth is essential for the success of any Martian colony. The average distance between Earth and Mars is about 225 million kilometers, leading to a communication delay of up to 24 minutes round trip. This delay necessitates the development of autonomous systems and local decision-making capabilities for the Martian colony. High-bandwidth communication satellites orbiting Mars could facilitate reliable data transmission, while undersurface cables might be used to establish a local internet network. Advances in quantum communication and deep space network technologies could further enhance communication capabilities, reducing latency and increasing data transfer rates. The establishment of a human presence on Mars will give rise to unique social dynamics and cultural developments. The first settlers on Mars will likely be highly skilled professionals selected for their expertise, adaptability, and ability to work in extreme conditions. These pioneers will lay the foundations for Martian society, developing the norms, values, and cultural practices that will shape life on the Red Planet. A sense of community and shared purpose will be vital for the psychological well-being of Martian settlers. Social activities, recreational facilities, and communal spaces will help foster social bonds and a sense of belonging. Over time, as the population grows and diversifies, Martian culture will evolve, influenced by the unique environment and experiences of its inhabitants. The governance of a Martian colony presents complex challenges. The legal and political frameworks established on Earth may not be directly applicable to Mars. Initial governance might be overseen by international space agencies and organizations with a focus on cooperation and shared objectives. As the colony grows, a more formalized governance structure will be necessary. Developing a legal system for Mars involves addressing property rights, resource management, and the rights and responsibilities of inhabitants. Questions of sovereignty and jurisdiction will need to be resolved, considering the Outer Space Treaty, which prohibits any nation from claiming sovereignty over celestial bodies. Martian governance could potentially become a new model of cooperative, multinational administration, emphasizing sustainability, scientific advancement, and the welfare of its citizens. Living on Mars will pose significant psychological challenges. The isolation, confinement, and distance from Earth can lead to feelings of loneliness, anxiety, and depression. To mitigate these effects, mental health support systems will be crucial. This includes access to mental health professionals, virtual reality environments that simulate Earth-like settings, and opportunities for social interaction and recreation. Designing habitats with natural light, green spaces, and communal areas can also improve mental well-being. Encouraging a sense of purpose and mission among settlers, along with regular communication with loved ones on Earth, can help maintain psychological resilience. The physical health of Martian settlers will be affected by factors such as reduced gravity, approximately 38% of Earth's gravity, radiation exposure, and the challenges of a closed environment. The lower gravity could lead to muscle atrophy and bone density loss, similar to what astronauts experience during extended stays on the International Space Station. Regular exercise and resistance training will be essential to counteract these effects. Radiation exposure is a significant concern, as Mars lacks a protective magnetic field and thick atmosphere like Earth. Shielded habitats, protective suits, and possibly the use of underground living spaces will be necessary to minimize radiation risks. Advances in medical technology, including telemedicine and regenerative medicine, will be vital for addressing health issues that arise on Mars. The development of a Martian economy will revolve around the utilization of local resources. Mining operations could extract valuable minerals and metals from the Martian crust, which could be used for construction, manufacturing, and possibly export to Earth. Water extraction and purification will be critical for sustaining life and industrial processes. Trade and commerce on Mars will initially focus on essential goods and services, with a barter system or digital currency facilitating exchanges. As the colony grows, a more complex economy will develop, potentially integrating with Earth's economy through the exchange of intellectual property, scientific data, and unique Martian products. Mars offers a unique environment for scientific research with the potential to make groundbreaking discoveries in fields such as geology, climatology, and astrobiology. Studying the planet's geology can provide insights into its history and the processes that shaped its surface. Climatological studies can improve our understanding of planetary atmospheres and climate change, both on Mars and Earth. The search for past or present life on Mars is one of the most exciting scientific pursuits. Discovering microbial life or evidence of past life would have profound implications for our understanding of life's origins and the potential for life elsewhere in the universe. Mars also serves as a testbed for technologies and strategies that will be essential for future human exploration of more distant worlds, such as the moons of Jupiter and Saturn. The colonization of Mars raises numerous ethical questions. These include the rights of Martian settlers, the potential impact on any existing Martian ecosystems, and the broader implications of human expansion into space. Ensuring the ethical treatment of all individuals involved in Martian missions, from selection and training to life on the planet, is paramount.